Thank you very much. So I thank Professor Goreski for this opportunity of the talk, and I thank Professor Taylor for inviting me. And I'm very glad to give a talk about my study on application of the theory of harmonic bundles to the study of holonomic D-modules, which I started about 15 years ago in this institute. And in my talk, many concepts and many theorems and many ideas originally go back to the professors in this institute, including Professor Griffiths and Professor Goreski and Professor McPherson and particularly Professor Dolini. So I'm very honored to talk about that. So anyway, so in this talk I will talk about a generalization of the decomposition theorem in to the context of semisimple algebraic holonomic D modules and some related progress. Sorry. So let me begin with D modules. So very roughly, D modules are essentially just systems of linear partial differential equations. So let me explain the definition very briefly. So we consider complex manifold denoted by X, and let dx denote the sheaf of holomorphic linear differential operators on X. And it is naturally a sheaf of algebras. And modules over the dx are called D modules on X. And strictly, we have to distinguish left modules and right modules. And in this talk, we consider only left D modules. Let me mention some easy examples. So dx itself is clearly D modules. And slightly more generally, the quotient of dx by left ideal is of course D modules. And holomorphic vector bundle with integral connection naturally give the D modules. I mean, integrable connection naturally induces an action of dx on the sheaf of holomorphic sections of the bundle, and it is naturally D modules. And in this talk, such D module is called flat bundles. So in particular, the structure sheaf, the sheaf of holomorphic functions is naturally D modules. And as I mentioned, D module is essentially a system of linear partial differential equations. For instance, we consider the D modules obtained as the quotient of dx by the left ideal generated by a differential operator P. Then morphisms from these D modules to OX naturally corresponds to holomorphic solutions of these differential equations. So in this sense, we can regard D modules as an intrinsic description of linear partial differential systems. So let me explain holonomic D modules, which appear in the title of my talk. So again, very roughly, holonomic D modules are appropriate generalization of ordinary differential equations to the several variable case. I mean, ordinary differential equations have many nice properties. For instance, the space of solutions is always finite dimensional. And such property is not satisfied for general linear systems of partial differential equations. But the holonomic D modules satisfy such properties. So in that sense, we can regard holonomic D modules as a generalization of ordinary differential equations. So anyway, let me explain the definition very briefly. So we consider the filtration of dx given by order of differential operators. Namely, let fj dx denotes the sheaf of holomorphic differential operators whose order is less than j. Then, multiplication of fj and fm is contained in fj plus m. So the associated graded object is naturally a sheaf of algebras, and it is naturally isomorphic to the symmetric product of the tangent sheaf. Then, for any coherent D modules, at least locally, we can find a filtration by OX coherent submodules, such that the multiplication of fj of dx and fk of m is contained in fj plus k of m, and we impose some additional technical conditions. Then, the associated graded object is naturally a module over the symmetric product of the tangent sheaf. So it naturally induces a coherent shift on the cotangent bundle of X. And the support is independent of the choice of filtrations, and it is called the characteristic variety of the D module. And it is known the dimension of the characteristic variety is larger than the dimension of X, which is originally due to Sato, Kashiwara, and Kawai, and later proved by Gaba in a much easier way. Then the D module is called holonomic if the dimension of the characteristic variety is equal to the dimension of X. So this is the definition of holonomic D modules. So very roughly, we impose some non-trivial constraints at any points at any directions. So let me mention some easy examples. The characteristic variety of the structure shift is the zero section of the cotangent bundle. So the structure shift is holonomic. And more generally, any flat bundle is holonomic. And the characteristic variety of dx is the cotangent bundle of x. So dx is not holonomic unless the dimension of x is 0. So dx is a very typical example of D module, but it is not holonomic in general. And let us consider the ordinary differential equation given by, for instance, this operator. Then the d equals 0 and d equals 1 is the singularity of the differential equations. And in this case, the characteristic variety of the corresponding D module is given as the union of the zero section and the 5 over 0 and 1. So the dimension of the characteristic variety is 1, and which is equal to the dimension of x. So this is a holonomic. So more generally, any ordinary differential equation gives a holonomic D module. Then we have many useful functors for holonomic D modules. For instance, if we are given a proper morphism of complex manifolds, say f from x to y, then we have the push-forward functor induced by f from the derived category of cohomologically holonomic complexes of D modules on X to the derived category of the cohomologically holonomic complex of D modules on Y. And let Fi dagger M denotes the ith cohomology object of the push forward of M by F. And let me remark, this push forward is not the same as the push forward of ordinary push forward of shifts or the push forward of all modules. For instance, if Y is a point, the target space is a point, then if dagger Im is equal to the I plus dimension x Drang cohomology of M, which is not equal to the cohomology of M. And let me mention in the algebraic setting, more strongly, we have 6 operations for algebraic holonomic D modules. So, for instance, if we are given algebraic morphism of algebraic manifolds, then we have 2 kinds of push-forward and 2 kinds of pullbacks. They are related by adjunctions and they satisfy some compatibility conditions. And we also have external product and inner homomorphism and duality and nearby and vanishing cycle functors. So we have many useful and powerful functors. So, for instance, if we are given some holonomic D modules, by applying these functors, we can construct many new holonomic D modules. And in particular, we have a subclass of algebraic holonomic D modules called geometric origin, which are whose objects are obtained from the structure shift of complex algebraic manifolds by applying these functors. Please?
Sorry, did you say what algebraic meant in this setting?
So I explained the complex analytic settings, but so we can also consider algebraic holonomic D modules. I mean, by using Zariski topology and algebraic differential operators, and we have the same thing similarly. And so there is a difference in complex analytic setting and algebraic settings. I mean, in algebraic setting, we have some intrinsically we have some natural compactification of the spaces. Not natural, but we have some family of compactifications. But in complex analytic settings, we don't have such ones. So there is some slight difference between them. So to distinguish them, we impose algebraic thinking. Sorry. Then let me mention some fundamental theorems in the study of D modules, that is Riemann-Hilbert correspondence. So by taking the tensor product of drum complex and D modules, and by taking the shift of degree by the dimension of x, we obtain a complex of shifts called the drum complex of the D module M. And according to Kashiwara, sorry. Sorry. This one. Sorry. Sorry, okay. So according to Kashiwara, if the D module is holonomic, then the complex is cohomologically C-constructive. I mean, we have stratification by complex subvarieties, and the restriction to each strata is cohomologically locally constant of finite rank. And moreover, he proved the complex satisfies the middle perversity condition, which is a vanishing condition for the cohomology along each strata. So we obtain the functor from the Z category of cohomologically holonomic complex of D modules on X to the Z category of cohomologically C-constructive complexes, and it is compatible with the natural T structure on the left-hand side and the T structure given by the middle perversity on the right-hand side.
So this is for X algebraic?
This is we have this functor for complex analytic settings. Yeah, actually, so to consider this object, we should maybe it's better to consider ordinary topology, I think. Sorry. Then thanks. Thank you very much. Sorry. So then Kashiwara and Mebuk introduced full subcategory of regular holonomic D modules, and they proved that the drum functor gives an equivalence of the cohomology category of cohomologically regular holonomic complex of D modules on X, and the cohomology. Regularity, I don't explain the precise definition, but regularity is a generalization of Fuchs type ordinary differential equations. I mentioned the holonomic D module is a generalization of ordinary differential equations. And
yeah. Several variables, what is it?
Sorry?
Have you defined it?
Sorry?
Did you define regular?
Yeah, I didn't explain the regularity condition, and I actually don't explain how to define regularity here, but it is a generalization of Fuchs type differential equations, ordinary differential equations. And so yeah, actually it's not so easy to define regularity precisely, but so anyway, so Kashiwara and Mebuk introduced regularity conditions, and if we restrict drum functor to full subcategory of regular holonomic objects, then this functor gives an equivalence. And actually it is compatible with other functors, I mean pull back and push back and push forward, and some other functors. So we can we don't have to distinguish regular holonomic complexes and C-constructive complexes, or we can identify regular holonomic D modules and perverse sheaves. Then, according to the celebrated decomposition theorem due to Beilinson, Bernstein, Dorin, and Graber, if M is regular holonomic D module on algebraic manifold X, which is semisimple geometric origin, semisimple means semisimple objects in the subcategory of geometric objects, geometric origin objects. And so if M is regular holonomic D module on X of semisimple geometric origin, then it's pushed forward by proper algebraic morphism is isomorphic to the direct sum of its cohomology objects in the derived category of regular holonomic objects. And and each cohomology object is again semisimple geometric origin. So this is a very important and amazing theorem, maybe in contemporary mathematics. So, for instance, it is very useful in various fields of mathematics, including representation theory and algebraic geometry and arithmetic geometries. And the proof is also very fantastic to me. So, Beilinson, Bernstein, Duringer, and Gaba worked for power shifts, which is equivalent to regular holonomic D modules, and they use the modulo P reductions, and so they go to the world of positive characteristic, and they applied the theory of power shifts with Frobenius instructions, and eventually they applied the value conjecture proved by Duringer. So the proof is very fantastic to me. So it's very deep and beautiful theorem in mathematics. And it also raises very interesting and rather philosophical but very important question. I mean, so according to a dictionary of Duringer, Cauchy structure should be the counterpart of Frobenius instruction in the algebraic geometry of a complex number field. So it is we can ask if we can prove this theorem within the world of a complex number field. I mean, without going to the world of positive characteristic by using Cauchy structure. And it was done by two methods, by Morihiko Saito and Cataldo and Migliori. And Morihiko Saito generalized this theorem to the context of regular holonomic D modules underlying pure polarizable Cauchy modules, or equivalently, regular holonomic D modules which are obtained as the intersection complex of polarizable variation of pure Cauchy structures by using his theory of Cauchy modules. And the work of Morihiko Saito establishes we have parallel theory of power shifts with Frobenius instruction on algebraic variety of positive characteristics, and power shifts with mixed Cauchy structures of algebraic varieties over complex number fields. So it is very interesting and strong and theory. And the work of Cataldo and Migliori is also very great and interesting. They gave an alternative proof of the original decomposition theorem by using the Cauchy theory in a completely different way. And their work brought us recently very exciting and new development in representation theory due to Williamson. So anyway, both are very interesting. Yeah.
Did you say what semisimple geometric origin meant?
Yeah. So if I understand correctly, so we have subclass of geometric origins. Geometric origin means so we obtain some holonomic D modules obtained from the structure shift of complex algebraic manifolds, applying 6 operations. So that is geometric origin. And semisimple means a semisimple object in the full subcategory of geometric origin, if I understand it correctly.
Yes, the point is that analytic fields are kind of infinite objects. So if you have a general analytic field, you have no way to transfer it to a finite field. While if it is coming from geometric origin, you have some finite data to define it, and then you can go to reduce modulo P and have the same data over a finite field.
Okay. Sorry. I'm sorry.
He's back.
Okay. Now, so we have a generalization of the decomposition theorem to the context of semisimple algebraic holonomic D modules. So for simplicity, we are suppose we are given complex project manifolds x and y, and suppose we are given morphism from x to y, and suppose we are given semisimple holonomic D module on x. Then it's push forward by F is isomorphic to the direct sum of the cohomology objects in the Z category of cohomological holonomic D module on X dx on X, and each cohomology object is again semisimple. And this was conjectured by Kashiwara. And there are two approaches to the decomposition theorem of semisimple pervasives or generally semisimple holonomic D modules. One is given by the method of arithmetic geometry. Actually, so Drinfeld proved a conjecture of Duyon implies the decomposition theorem of semisimple pervasives, and Gaisgori and Beckel-Kare proved the conjecture of Duyon independently. So the decomposition theorem of semisimple pervasives was also proved.
Is this a theorem or a conjecture?
Sorry?
Is this a theorem?
This is theorem, and
Conjectured by Kashiwara conjectured it.
yeah. So originally, this statement was conjectured by Kashiwara. Yeah.
And what is the difference between this theorem and the one on the previous slide? That seems that the geometric origin is replaced by holonomic.
Yeah. So in the previous theorem, sorry, I'm wrong. It is so the statement is very similar, but this calls for subclass of geometric origins. So in particular, this implies the D module is assumed to be regular singular, but in this generalization, we don't have to assume, for instance, regular singularities, just semi-simple, and so the category is much wider than the and we have the other method to approach this theorem using generalized Hochi theory on holonomic D modules, which was developed by Kurosawa and myself. And I'd like to explain this second method in the rest of my talk. So to prove this type of theorem, we need some structure. I mean, we need to enhance holonomic D modules with some structure. As I mentioned, Beilinson, Beilstein, Drin-Gaba used Froben instructions, and Moriko Saito and Cataldo Miglioni used Hochi structures. And for me, the work of Moriko Saito is a model. So let me comment something more about his work, the work of Moriko Saito. So Moriko Saito introduced and established the theory of mixed Hochi modules, which roughly means regular holonomic D modules enhanced with mixed Hochi structures. But it is very difficult and challenging problem to define mixed Hochi structure in the context of regular holonomic D modules. And he introduced very nice idea using nearby cycle functors and vanishing cycle functors. And he solved many problems to prove his work worked well. And in particular, he proved the the functoriality and hard-left theorem for regular for polarizable pure Hochi modules with respect to the push-forward by projective morphisms, which implies the hard-left theorem for regular holonomic D modules underlying polarizable pure Hochi modules, which implies the decomposition theorem for projective morphisms for this type of regular holonomic D modules. So this is a model for me. But anyway, so we need some structure. We have to enhance holonomic D module with some structures. And for holonomic D modules, we use generalized Hochi structure instead of ordinary Hochi structure called twistor structure, which was introduced by Carlos Simpson. So let me explain twistor structure. Twistor structure is just a holomorphic vector bundle on P1. And mixed twistor structure is a twistor structure equipped with an increasing filtration such that the JS graded piece is isomorphic to the direct sum of OP1J. And we regard mixed twistor structure as a structure on the vector space of the best vector space obtained as a fiber over 1. So this is the twistor structure. And as I mentioned, twistor structure is a generalization of Hochi structure or underlying structure of Hochi structures. And more precisely, Simpson proved complex Hodge structure is equivalent to C-star equivalent twistor structure. So let me mention how we can obtain a twistor structure from a complex Hodge structures. And the complex Hodge structure is just a vector space, C vector space with two decreasing filtrations. So by applying the least construction to the vector space with one filtration, for instance F, then we obtain a free C lambda modules, and it gives a vector bundle on spec C lambda. And similarly, by applying the least construction to the vector space with another filtration G for variable lambda inverse, we obtain vector bundle on spec C lambda inverse.
What is G?
G is just a filtration. So usually, so Hodge structure is defined as Q vector space and Hodge filtration on the vector space tensor C. So by taking the adjoint, by taking the conjugate, we have another filtration. And in complex setting, we give two filtrations from the beginning. So by gluing two vector bundles, we obtain vector bundle on P1. So in this way, we obtain a twistor structure from a complex Hodge structure. And in this case, we have some gradings, so we can see the vector bundle is equipped with C star, natural C star action. And Simpson proved this gives an equivalence of complex Hodge structure and C star equivalent twistor structure. And he proposed a principle called Simpson meta theorem, which roughly says any concepts and theorems concerned with Hodge structure should have their generalization to the context of twistor structures. So this is called meta theorem because Simpson gave a statement as a meta theorem, but I regard this one as a principle.
So it should be a meta conjecture.
No, I mean for the conjecture, we need maybe we need more precise statement. But
Why is this thing a free C lambda module?
so this is torsion free because this is contained in C lambda H C lambda inverse, and the point is this is finite dimensional, and because F is decreasing, and sorry, maybe so I have to assume F is complete. I mean if J is very large, then Fj should be 0, and if we import such condition, then this is finitely degenerated. Okay. Then, so for the generalization of the decomposition theorem, we have two main issues. One is to establish the theory of twistor version of Hodge modules, which should be the theory of holonomic D modules enhanced with twistor structures. And we can expect the existence of such theory according to Simpson's meta theorem. And the other issue is to relate or characterize the semi-simplicity for algebraic holonomic D modules by the existence of polarizable pure twistor structure on the algebraic holonomic D modules. So once these two issues are done, then so we have the functionality of polarizable pure twistor structure by the push forward by projective morphisms, and translating it to the semi-simplicity condition, we obtain the functionality of the semi-simplicity condition with respect to the projective morphisms, and which should imply the decomposition theorem for semi-simple algebraic holonomic D modules. And maybe it's instructive to explain these two issues. If everything is smooth, I mean for flat bundles and for smooth projective morphisms, these two issues were established by the previous work of Simpson and Collett. Actually, when Simpson introduced the concept of twistor structure, he also introduced the concept of polarized variation of pure twistor structure as a twistor version of polarized variation of pure Hodge structure. And he also, moreover, he established the equivalence of polarized variation of twistor structure and harmonic bundles. And so I don't explain the precise definition of polarized variation of characteristic structure in this talk, but let me explain harmonic bundles. So let me explain harmonic bundles. So we consider a holomorphic vector bundle on X, complex manifold X. And let theta denote the Higgs field, which means theta is a holomorphic section of n e tends omega 1, such that theta square equals 0. And if we are given a Hermitian metric of the vector bundle, then we have the charm connection, which is the unitary connection determined by the holomorphic structure and the metric. And we have the adjoint of Higgs field with respect to the metric H. And by taking the sum of the charm connection and the Higgs field and its adjoint, we obtain a connection denoted by D1. Then, if this connection is integrable, I mean the curvature vanishes, then the metric is called purely harmonic metric of the Higgs bundle. And the tuple of Higgs bundle and purely harmonic metric is called harmonic bundle. And let me mention, if the base space is one-dimensional, this condition is equivalent to the so-called Hitchin equation. And as I mentioned, Simpson established the equivalence of harmonic bundles and polarized variation of pure-twistor structure. And as I explained, twistor structure is a holomorphic vector bundle on P1.
Sorry, I'm falling behind you.
Yeah.
So what exactly was a harmonic bundle? It was.
It's better to.
You could go back
Yeah.
No section. Harmonic. The notion of harmonic is just for the bundle. What's the equation?
Equation is this is the equation.
What's the equation?
Yeah.
The equation.
The equation. So this is the equation for this metric. So this gives the condition for metric, and if this is satisfied, the metric is called pure harmonic metric. And so this vanishing is the vanishing of two forms. And so we have the decomposition of 2-0 part and 1-1 part and 0-1 part. And 1-1 part is these conditions. And if the base space is one-dimensional, we always have the vanishing of 2-0 part, 2-0 form and 0-2 form. So in that case, this condition is equivalent to this one. And so harmonic bundle is just
caught up with you.
yeah. So this name is rather strange because this is called pure harmonic metric. So maybe it's better to call pure harmonic bundle, maybe, but it is called harmonic bundle. Okay. So as I mentioned, Simpson established the equivalence of harmonic bundles and polarized variation of pure twistor structure. And the twistor structure is a vector bundle on P1. So this should be something on P1 times X. So let me measure how a harmonic bundle on X induces something on P1 times X. So suppose we are given a harmonic bundle on X, and as I explained, we have 1-0 delta del H, which is the 1-0 part of the charm connection, and the adjoint of theta with respect to H. Then we have the family of integrable connections parameterized by non-zero complex number lambda in this way. If lambda equals 1, this is integrable connection by the definition of harmonic bundles. And but for non-zero lambda, actually this gives integrable connection. And we cannot extend this family of integrable connection across lambda equals 0 and lambda equals 0 or lambda equals infinity, at least naively, or as a family of integrable connections in general. But if we multiply lambda on 1-0 part, and if we consider the family of differential operator given in this way, so this is obtained from this one by multiplying this part by lambda. Then this is extended to the family of, this is extended across lambda equals 0. And at lambda equals 0, this is no longer flat bundle, but Higgs bundles. I mean, at lambda equals 0, we have this part vanishes, so just del E bar and theta. This gives the Higgs bundle. So by considering the degeneration to Higgs bundle, we can extend this family across lambda equals 0. And similarly, by considering the degeneration to the Higgs bundle of the conjugate of X, we can extend this family across lambda equals infinity. So in this way, we obtain something on P1 times X. And this is a variation of pure twistor structure. And by refining this construction, we can obtain, or Simpson obtained, the equivalence of harmonic bundles and polarized variation of pure twistor structures. Let me remark, harmonic bundle does not contain anything about the information of weight. We can always twist weight by any integers. So if we fix some weight, we have equivalence of this equivalence. Then Simpson proved the functoriality of harmonic bundles for smooth projective manifolds. I mean, so he proved many important theorems for polarized variation of Hodge structures can be generalized to the context of harmonic bundles. For instance, he studies the harmonic analysis for harmonic bundles as a generalization of the harmonic analysis for polarized pure Hodge structures due to Green. And for instance, if we are given smooth means submassive ones and smooth project morphism, and so if we are given harmonic bundle on X, then and if we take relatively ample line bundle L of X, then so as a push part of the underlying flat bundles, we obtain flat bundles on Y. And he proved the morphism from here to here by induced by the first rank class of L is an isomorphism. So this is a hard representative theorem for in these situations. And he also proved we have the naturally induced harmonic bundles obtained as the push forward of this harmonic bundle over whose underlying flat bundle is naturally isomorphic to the push forward of the underlying flat bundles. So maybe in other words, the push forward of flat bundles by smooth project morphism is enriched to the push forward of harmonic bundles. That is what he proved. And as for the characterization of semisimplicity, let me mention the fundamental theorems in the study of harmonic bundles. So by definition, harmonic bundles have the underlying Higgs bundle and the underlying flat bundle. And according to Collett and Simpson, if the base space is smooth projective, then this correspondence induces the equivalence of harmonic bundles and Higgs bundles and flat bundles on projective manifolds. Precisely, we should impose some conditions. Actually, so Simpson proved the equivalence of harmonic bundles and Higgs bundles which are polystable and have trivial Chern characters. I mean, so the CH0 is always rank of E, so this means the vanishing of higher Chern characters. And I don't explain stability condition here, but this is the most classical stability condition, sometimes called slope stability or something like that. And Collett proved the equivalence of harmonic bundles and semisimple flat bundles. So here we have semisimplicity condition. Then we can obtain the decomposition theorem in the case where everything is smooth. I mean, if we are given semi-simple flat bundles and smooth morphism of smooth projective manifolds, then we have the corresponding flat harmonic bundles, and we have, according to Simpson, we have, so according to Collett, we have the corresponding harmonic bundles And according to Simpson, we have the push forward of harmonic bundles, which is compatible with the push forward of flat bundles. And again, according to the theorem of Correct, we obtain and we also have Hard-Left system harmonic bundles. And again, the theorem, according to the theorem of Correct, we have the semi-simplicity of the push forward of the flat bundles. So if everything is smooth, we can obtain the decomposition theorem from the previous works of Correct and Simpson. So what we would like to do is to generalize this story to the singular case. So as I mentioned, we have two issues. One is to establish the theory of twistor version of Hodge modules, which should be the theory of holonomic D modules enhanced with twistor structures. And we would like to relate or characterize the semi-simplicity condition and the existence of polarizable pure twistor structure for algebraic holonomic D modules.
Your theory non-trivial even in the ordinary differential equation case where you don't have regular singular cases?
Yes. But in the one-dimensional case, there are some previous works. For instance, Biccar and Borchi established the equivalence of stable wild harmonic bundles and stable filtered bundles. But anyway, so even in the one-dimensional case, this is
not different there?
Yeah.
Or your method's new in that case as well?
Yeah, I think so. But okay. So let me explain. So twistor version of Hodge modules is called twistor D modules, which was introduced by Claude Sava and studied by him and myself. And we can summarize the theory by two main results. So one is the functoriality of pure and mixed twistor D modules. So in the pure case, we have the push forward of polarizable pure twistor D modules by projective morphisms. And we also have hard-left theorem for polarizable pure twistor D modules by projective morphisms. And in the mixed case, we have 6 operations on the derived category of algebraic mixed twistor D modules, which are compatible with the 6 operations for algebraic holonomic D modules. And the other main result is the description of pure objects and mixed objects. I mean, the definition of pure and mixed twistor D modules are rather complicated. So it's useful to have which objects are really contained. And in the pure case, polarizable pure twistor D modules are the this is not so precise expression, but very roughly, polarizable pure twistor D modules are the minimal extension of variation of wide variation of polarizable pure twistor structures. And in the mixed case, mixed twistor D modules are expressed at least locally as the gluing of admissible variation of mixed twistor structures. And these are generalized or twistor version of the theorem of for Hodge modules, and the most essential ideas were given by Mohiko Saito in the context of Hodge modules. So the ingredients for Hodge modules and twistor D modules are not the same, and some phenomena occur only in the pure twistor case, only occur twistor case. I mean, some phenomena does not occur in Hodge case. So we cannot apply his results directly, but we can use his ideas even in the twistor case. And let me also mention the local theory of wide harmonic bundle is very fundamental in this kind of study, which I will explain later. So let me mention hard-left, and the decomposition theorem is related with hard-left theorem for pure polarizable pure twistor D modules. So let me mention it. So, suppose we are given projective morphism with a relative unprime bundle L, and suppose we are given polarizable pure twistor D module on X, and if M is, let M denote the underlying holonomic D module on polarizable pure twistor D modules, then so as in the case of harmonic bundles for smooth projective morphisms, we have a naturally induced polarizable paired-twisted D modules of whose weight is shifted by I, and whose underlying holonomic D module is naturally isomorphic to the push forward of M. So the push forward of holonomic D modules by projective morphism is ended to the push forward of polarizable paired-twisted D modules. And and we have the Howard-Lexus theorem for polarizable paired-twisted D modules, which implies for the underlying holonomic D modules, the morphism from here to here induced by the first Chern class of L are isomorphism for any non-negative J. And as for the characterization of semi-simplicity on any projective manifold, we have the correspondence of semi-simple holonomic D modules and √-1 R polarizable paired-twisted D modules. √-1 R means very roughly, polarizable paired-twisted D module corresponds to wide harmonic bundles, which I will explain later. But so this condition very roughly means the eigenvalues of the residue of Higgs field are purely imaginary. So we have subclass of polarizable paired-twisted D module called this one. So we have this type of characterization of semi-simplicity of holonomic D modules if the base space is algebraic. And for this correspondence, we need to establish the correspondence of √-1 R polarizable paired-twisted D modules and √-1 R wide harmonic bundles, and the correspondence between √-1 R wide harmonic bundles and semi-simple meromorphic flat bundles. So this correspondence is essentially the description of paired-twisted D modules. So we have to establish this correspondence. And for this, we have three issues.
Sorry, this correspondence is on what sort of manifold?
Sorry, this is given on projective manifold, or or algebraic manifold. I mean, we have to impose algebraicity or for this type of characterization of semi-simplicity.
But there are singularities. It's not a local system. It's like can be like the direct image of a local system. So
These objects.
Yeah. So semi-simple holonomic D modules are obtained as a minimal extension of semi-simple meromorphic flat bundles on smooth subvarieties which are not closed. So we have some singularity of. So we have to study singularities of these objects.
Will you tell us what wild harmonic bundles are?
I will explain it just after this slide. So for this we have three issues. So one is local theory of wide harmonic bundles around singularity, and we have to study the global theory of wide harmonic bundles on projective manifolds, which should be the generalization of the correspondence of Collector and Simpson, which I explained in the smooth case. And we also have to study the irregular singularity of meromorphic flat bundles, so which I will explain in the rest of my talk. So let me explain wide harmonic bundles. So we consider complex manifold equipped with a normal crossing hypersurface, and we consider harmonic bundle given on the complement of D, the hypersurface. Then the Higgs bundle naturally induces a coherent shift on the cotangent bundle of X minus D, and the support is called support of the coherent shift. So this is a subvariety of the cotangent bundle of X minus D, and anyway, this is called spectral variety of the Higgs bundle or harmonic bundle. And if the closure of the spectral variety in the logarithmic cotangent bundle is proper over X, then the harmonic bundle is called tame. And if the closure of the spectral variety in the logarithmic cotangent bundle twisted by OND is proper over X, then the harmonic boundary is called wild. So wild is a bigger class of harmonic boundaries. And very roughly, tame harmonic boundary should correspond to Melon flat boundary with regular singularities, and wild harmonic boundaries should correspond to Melon flat boundaries, which are not necessarily regular. And so, for instance, if we are given meromorphic function, then we have the associated wide harmonic boundaries, which is harmonic boundary of rank 1, and it is just this trivial vector boundary, but the fixed field is given in this way, the differential of f, and the metric is given in this trivial way. And polarized variation of complex Hodge structure always gives a tame harmonic boundaries, because the Higgs field of variation of Hodge structure is always nilpotent. And so let me remark, for the analysis of wide harmonic boundaries, we should impose a non-degeneracy condition on the spectral variety along the hypersurface D. But it is not so restrictive, because we have some projective birational morphism, if we take the harmonic boundary by, if we take the pullback of the harmonic boundary by the projective birational morphism, then this condition is satisfied. So this is not so restrictive. But yeah. So let me explain the local theory of wide harmonic boundaries, which is a twisted version of the study of the asymptotic behavior of polarized variation of Hodge structures. So let me remind you two important theorems from the study of the asymptotic behavior of polarized variation of Hodge structures. So one is the extension of polarized variation of Hodge structure on x minus d to a melomorphic object on xd. I mean, so variation of Hodge structure consists of flat boundary and Q structure and Hodge filtrations and polarizations. And flat boundary is always extended to vector boundary with local-specific connection called the Doreen extension. And but it is highly non-trivial if we can extend the Hodge filtration to the filtration of the Doreen extension or not. And but it is known as a consequence of the nilpotent orbit theorem of Schmidt. so anyway, so we can extend polarized variation of structure on x minus d to some melomorphic object on xd. That is a very important step in the study. And the other is the existence of limit polarized mixed Hodge structure at each point of d. So by the data of the Hodge filtration at the point, we obtain some Hodge structures and weight filtrations, and according to SL2 orbit theorem of Schmidt in the one variable case, and according to Kaplan-Schmidt in the several variable case, that gives the limit of polarized mixed Hodge structures. And the existence of limit polarized mixed Hodge structure ensures the melomorphic object has very nice property along the hypersurface D. So these steps are very important. For instance, the application of the study of the asymptotic behavior of polarized variation Hodge structure to the theory of mixed Hodge structures. And in the wild case, in the case of wide harmonic bundles, we have the twisted version of this kind of theorem results. So the important result is, so we can extend wide harmonic bundle, which is given on x minus d, to a melomorphic object on xd. And we also have a sequence of reductions from wide harmonic bundles to a polarized mixed Hodge structure, and which ensures the melomorphic object has nice property along the hypersurface D.
What does that last sentence mean? Reduction?
Sorry?
What does this reduction comment? I didn't
So let me explain something about it.
Will this melomorphic structure make it algebraic in some sense?
Yes, I don't know. I mean, so maybe not algebraic. I mean, so even if we consider algebraic melomorphic flat boundary, we should consider something on C so if you are given something on algebraic object on X, we should consider something on C times X or P1 times X. And if we consider such C object on C times X, it's not algebraic, I think, in general. So, so maybe we need to define the appropriate algebraicity in this context. So anyway, object itself is not algebraic in the naive sense, I think. So anyway, so let me explain prolongation result. So it's not difficult to explain the full statement of prolongation result, but to very roughly, so as I mentioned, we have the family of lambda flat bundles, and so this is given on X minus D.
So did you say what good means?
Yeah, sorry. So this means, so as I mentioned, we have to assume some non-degenerate condition on the spectral variety along D, and that is goodness. Yeah. So sorry. So this is, so we need some assumption on the spectral variety of wide harmonic bundles. But please.
And everything you're saying for wild harmonic bundles is also true for tame ones. Right?
Yes.
Is there bundles that are not wild and not tame?
No. Wild implies tame. So tame harmonic bundle is a subclass of wild harmonic bundles. Yeah. Sorry. So tame is easier, and so it's maybe it's.
To clarify a question, in your main theorem, you
Yeah.
have no assumptions about regularity. So wild is the worst situation.
Yeah, so for the statement made, wild is but so tame is important at least in the intermediate steps, or so it's better. So in the study of merely flat bundles, it's convenient to consider to have the subclass of regular singular merely flat bundles. So I explained the tame case also. Okay, so anyway, so maybe I have to finish my talk soon. So sorry. So anyway, so we have family of flat bundles, lambda flat bundles, and this is so wild harmonic bundle is just given X minus D. So this is just given X minus D, but this is extended or prolonged to monotonic lambda flat bundles on XD, and similarly we have lambda inverse flat bundles on the conjugate, and this is extended to monotonic lambda inverse flat bundle on the conjugate X dagger and D dagger. And so we have some family of monotonic lambda flat bundles and monotonic lambda inverse flat bundles, and this is very not easy to explain, but so we have stock structure on this monotonic lambda flat bundles, which is given as a family of filtrations on sectors, and so we have two extensions, but and they are not compared directly, but stock structures are same, so we can regard them they are same. So so in that sense, they give something on P1 times X, and KMS structure is given a family of filtration and decomposition on D, which is induced by the parabolic structure and the residue of D lambdas. Maybe I will explain this one in another talk. So anyway, we have some structures on this one, and the point is, so stock structure is given as a family of filtrations, which is not given globally, but just filtration sectors. But so if we take associated graded object, then we can group them and we can obtain the global graded object. And we have something similar for KMS structures. So we have some reductions from the original one with respect to the stock structure or KMS structures. And so taking the associated graded object with respect to the stock structure and the KMS structures, the structure of wide harmonic bundle is much simplified from the original ones, but they give some very nice approximation of the original object. So by using this kind of sequence, we can reduce the study of wide harmonic bundles to the study of, also very roughly, we can study the study of polarized mixed Hodge structures. And but we can conclude the meromorphic object has very nice property along the hypersurface. So this is a very rough story of local theory of wide harmonic bundles. And in the global theory, the global theory is generalization of the theorem correct. I mean, the characterization of semi-simplicity of Melon-Flat bundles in terms of wide harmonic bundles. So this theorem is a Melon-Flat bundle on Xt is semi-simple if and only if it is obtained as the prolongation of root minus 1 are wide harmonic bundles. But we have some technical problem about this theorem. So as I mentioned, for the analysis of wide harmonic bundles, we have to assume some non-degenerate condition of the spectral variety along the hypersurface T. And for the analysis of Melon-Flat bundles, we have to impose similar condition, which is called the problem of turning points. And sorry. So I finished. I'd like to mention the problem about the irregular singularities. So the study of regular singularity in the high-dimensional case was established by the study of Professor Dorin. And in the irregular case, the irregular singularity in the one-dimensional case is very classical, but the higher-dimensional case was established rather recently after the work of several people. And roughly, it is generalization of the theory of one-dimensional case, but we need some additional steps. I mean, in the one-dimensional case, the study of Melon-Flat bundle consists of 3 steps. One is the study of formal decomposition. I mean, if we take formal completion, then after runtime covering, Melon-Flat bundle has a very nice decomposition called Fukara-related tilting decomposition. And so it is just the direct sum of regular singularities treated by Melon-Flat functions. So this is the formal structure is very easy. And the decomposition is not extended across the neighborhood, but we can extend the decomposition to sectors. And that is a symptotic analysis. And the decomposition is not unique, but filtrations are canonically defined. So we have led to the notion of Stokes structures. And then we can classify Melon-Flat bundles in terms of local system with Stokes structures, which is general Riemann-Hilbert correspondence. And in the high-dimensional case, we need an additional step before the one. I mean, we have to take projective birational morphism, and we have to take the pullback by birational projective morphism to simplify the structure. But the existence of such birational projective morphism is not easy to prove, but it was conjectured by Sava and proved by Kedrai and myself. And it is also useful in the study of semisimple Melon-Flat bundles, the characterization of semisimplicity of Melon-Flat bundles. Sorry, I have to emphasize the result of Kedrai is more general. I mean, his work is also available for complex analytic setting, and my result is just for algebraic case. Anyway, so on any smooth projective varieties, we have the correspondence of semisimple Honic D modules and polarizable root minus 1 pure theta D modules. And we also have functoriality of polarizable pure theta D modules, which is compatible with the push forward of D modules. So, and we have how do you this theorem? So by applying these results to we obtain the decomposition theorem of semisimple holonomic D modules. So I finished my talk. Sorry. Thank you very much.